But you see there's a symmetry to this normal distribution, and so a z-score of -2 would be a tail probability of 2.28%. On this side, 2.28%. Let me write that a little more legibly. I can't find my eraser, so I had to use a dish towel for this video. Alright, so people within 2 standard deviations of the mean would be 100% minus these 2.28s. Now let's see, if I multiply this by 2, I get 4.56%. If I subtract that from 100%, I get 95.44%. So the number of people who have IQs between 70 and 130 happens to be 95.44%. All right. And you might say, well, but the empirical rule says I should be 95%. Yes, it does. The empirical rule says that, but that's just kind of a rule of thumb. It's kind of a rough guide. And the more precise number, 2 standard deviations, is actually 95.44% lie between those 2 numbers. Okay. Actually, if you want to get the middle 95%, it's going to be 1.96 standard deviations. Okay, now how did I know that? Besides having taught this course a lot. Well, if you look on this little chart on the left side of the paper, and it says value of z for tail probabilities from 0.50 to 0.01. All right. Now, if I wanted the middle 95%, that means this is going to be 2.5%. This will be 2.5%. 2.5% is 0.025. So on this little chart, look for 0.025. Now what number do you see beneath it? 1.96. So 1.96 is the more precise number that describes the middle 95% of a normally distributed population. All right. Anyway, give you some idea there. The as far as IQ, let's do another calculation. It's said that the genius level, at least as rated by, I think, by Mensa organization. I don't know if all the psychologists agree on this. Geniuses are comprised of the top 1% of the population. Well, it turns out that would be an IQ of about 135. And so let's look at that. If x was equal to 135, then the z-score would be 135 minus 100 divided by 15. So this is 35 points above the mean. And if a standard deviation is 15 points, then 35 divided by 15 is 2.33. 2.33. So the top 1% happen to be 2.33 standard deviations or greater above the mean. This would be 1%, that tail probability. So let's verify that on the chart. Let's find 2.33 because you need to be able to learn how to read this chart. And 2.33, we would go 2.3 down the left-hand column, find 2.3. Then the second decimal place is also a 3. So I go across to the 0.03 column, which is the fourth column in the white and black area. So 2.33 gives us a tail probability of 0.0099. So I'm slightly off. It's not quite 1%. It's 0.99%. All right. Well, that's the closest you're going to get to 1% by using 2 decimal places for z-scores. Now I should tell you, all z-scores are always calculated with 2 decimal places, at least in statistics courses. And I suppose if you're using a statistical package that calculates things, they would go more decimal places and it would do the calculus for you. By the way, this chart is these numbers in the chart, the z-score chart in the white and black area, are area calculations under a curve. And if you've had calculus, you'll recognize that as an integration. In this case, we're integrating from 2.33 to infinity, and of this function, and I'll tell you this function in the next chapter, what that function is. And so that integration would give you this area number. All right. Well, most people taking this course have never seen calculus, so we don't have to bother with that. We just have these convenient charts because no one would want to look at, have to do the calculations anyway each time. All right. So please don't get in your head that all standard deviations are 15 and all means are 100. This is only the IQ example that I'm using. So anyway, kind of introduction there into the z-score. All right, now I want to tell you a few other things here. I'm technically a little bit off here by calling this x bar and this s. All right, so I hate to confuse matters, but I need to. We actually have 2 means and 2 standard deviations that are used in statistics. And the mean used for a population is the Greek letter mu. So here's what a mu looks like. In Greek, mu is kind of like an upside down H. Mu represents the population mean. So if I were to take a full census of a population, that would be, and take its average. The average of a full population is called the population mean. And to represent that, we would use Greek letter mu. All right, so actually, in fact, the IQ test, because the mean is always 100, that's considered a population mean. And so, more technically, I should use letter mu for that. All right, now, we virtually always encounter the sample mean. And the sample mean, I've used this symbol before, x with a bar over it, is known as the sample mean. All right, so we have a Greek letter for population, we have an English letter for sample, and that goes across all the statistics we do this quarter. You'll encounter a couple of Greek letters, and there'll be corresponding English letters. Greek letters are always population, English letters are always sample. All right, these are calculated the same. Calculated the same. So you wonder, well, why do we need 2 of them? Okay, well, actually, we use Greek letter mu in a different context most of the time. Most of the time, it's a comparison value rather than a population mean. We're comparing some set value to sample data, and the Greek letter mu will represent this comparison value. So that will begin to make more sense as we move through other chapters.